Hello and welcome to the first ever episode of the Chemistorian podcast. I've got a great interview coming up for you with the world's leading expert on the periodic table, Professor Eric Scerri. Eric is a chemist and historian who has dedicated a large part of his illustrious career to the study of the periodic table. And as a result, in 2015, he chaired an official committee to decide which elements should go into Group 3 of the periodic table. So not only is he an expert on its history, he has directly influenced what the periodic table looks like today. I had a fascinating conversation with him. Prepare to learn about the origins of what we call elements, the curious concept of chemical triads, the earliest attempts at organizing the elements, the legendary predictions made by Dmitri Mendeleev, and much more. We even stumbled upon an exciting historical discovery during our conversation. I hope you enjoy. The main question I want to start with is it fair to say that you are the world's leading expert on the periodic table?
Well, I'm not the one to answer that question, but it has been said.
That's a very modest way of answering that question. Great. Okay. So not only are you an expert, if not the expert on the history of the periodic table, you have personally influenced the periodic table as it exists today. Could you tell us a bit about that?
Well, I'm not sure how successful I've been in doing that. I've certainly proposed modifications to the periodic table. I've proposed what I consider to be the optimal, best possible periodic table. Chemists are typically rather reluctant to accept modifications, especially to something as fundamental as the periodic table. So yes, I've made proposals, but I wish they'd been taken up more seriously. Again, and on this, I'm not being modest. I'm just saying it like it is.
Okay, fair enough.
We can get into the details at some point if you're interested. But
I very much am. Yeah, I'd like to dive into this and make a whole video about your contribution towards Group 3. But that's a whole different story. I could dedicate a whole video to that. So if anyone's watching, please let me know in the comments if you'd like to see that. It's a great story. I'm assuming related to this, you were named by Academic Influence as the second most influential chemist of the decade between 2010 and 2020. How did that feel?
Oh, it felt very good. It was rather unbelievable because I don't do actual hands-on chemistry research. I talk about the historical aspects, philosophical aspects, educational aspects, but I don't do any actual chemistry where you're manipulating molecules, inventing new products or what have you. So I was a little surprised. It turns out it's because I have a strong internet presence. That was partly contributed to being rated as the second most influential chemist of the decade.
So clearly the periodic table is something that really fascinates you. What do you think it is that draws you to the periodic table so much?
Okay. Let me put it this way. Growing up, my first hobby was stamp collecting. What I liked about stamp collecting was the exactitude of it, the classification aspect of it, where you would have to, first of all, separate different countries, and then you would have a set of stamps and you would lay them out nicely in a stamp album. So there was classification. The periodic table is, of course, the ultimate natural system of classification. It appears that nature itself has decided to put the elements into classes or groups of similar elements. And it's a remarkable situation because these are quite different elements. They're quite separate. Each have their individuality, and yet there is a very powerful sense in which they belong in sets together, to pursue the stamp collecting analogy. So I've always been drawn to classification. I've been drawn to systematization. And and this is a common experience among people who've studied chemistry, perhaps you had the same experience. that when you begin to learn chemistry, it's all a jumble of facts with little connection. When you're presented with the periodic table, as I was as a student, I think in the sixth form, all of a sudden things fall into place, literally fall into places on the periodic table. And it all begins to make much more sense. It's a connection. It's a unifying system. So for all those reasons, I find it extremely interesting.
You know, studying chemistry or history teaches you to see patterns in molecules, in civilizations, and in people's lives. And one pattern I see a lot lately, smart, capable people feel stuck. They've got degrees, they're working hard, but their jobs aren't paying enough, there's no growth, no perspectives, or they're just burnt out. But what if I told you it's possible to effectively transform your career? Meet TripleTen, the beginner-friendly bootcamp designed for people who want a real career change, especially into tech, but don't have the time or finances to drop everything and go back to university. TripleTen's part-time online programs fit seamlessly into your schedule. With courses spanning from 4 to 10 months, you'll work on real-life projects under the guidance of experienced tutors, building a portfolio that stands out to employers. And here's the most amazing part of all. TripleTen offers a 100% money-back guarantee. If you don't land a relevant tech position within 10 months of graduation, you'll receive a full refund. Ready to catalyze your career transformation? Visit the link in the description to get a free career consultation and use my code CHEMISTRY to save up to $3,400 on your education now. Yeah, it's actually I've been having similar thoughts about this recently, just thinking about what is it that draws us to the periodic table. And I had this idea that I wanted to get your opinion on. But when we think about the beginning of the universe, we think about the Big Bang and this huge, unfathomable explosion and how it's just complete chaos, essentially. That's, energy and matter forced into existence and blasted outwards completely randomly. And this really is just chaos in its purest form. But somehow what was birthed in that random explosion coalesced into particles that, when categorized, show anything but chaos. And they have these consistent repeating patterns, every few elements, as you said, and these predictable trends in properties that are very easily quantifiable. So would you say that it's this order from chaos that seems to be the most fundamental implication of the periodic table, and that's why it's so important to us?
I've never thought of it quite like that. I suppose that's true. And of course, that could be extended to other areas. I mean, the existence of life. Life is relatively ordered, depending on what country one lives in and so on. At the moment, things are quite disordered where I live, but that's another matter. So, yes, order out of chaos is one aspect. I've never thought of it like that.
Yeah, it's something I was mulling over in my head. So before we dive into the history of the periodic table of elements, it seems like a good idea to define what an element is. So how do we define it today, and how did that definition come about?
Okay. Now, this is a somewhat complicated issue, and it's an issue which has been much debated in the philosophy of chemistry, my area of research. The ancient Greek philosophers, the pre-Socratic philosophers, had a view that there were four elements: earth, fire, water, and air, and that all the things we see around us were essentially made of these four elements. So these four elements, as well as existing literally in that we have water, air, and fire, and so on, were somehow components of everything we see. And there were different combinations of these things that are observable. That's a sort of rather metaphysical view of what elements are. Elements, they were sometimes called elements as bearers of properties, but not themselves having properties. As we all know, the ancient Greek philosophical ideas on science were interesting, but were not very productive. it had to wait something like 2.5, 3,000 years before science got off the ground. And science got off the ground in the scientific revolution, in the chemical revolution, by turning away from these more metaphysical views to looking at what could actually be measured, what could be observed. Right? So there was a very sort of strong positivism that ran through what we call modern science. In the case of chemistry, Lavoisier, regarded as the father of modern chemistry, took the step of defining elements as the last stage of purification or simplification. If you can't break something down any further, you have reached the stage of it being called an element. Now there's no talk of metaphysical elements, if you like. It's not an abstract view, it's a very concrete view of elements. Now, based on that, there was tremendous progress. Similarly, in other areas of science, if one could measure things, if one could experiment, unlike what the Greeks had not done, progress was to be had. However, the more abstract view of elements did not completely die away, and it was revived, interestingly enough, by the leading discoverer of the periodic table, Dmitri Mendeleev, who is well known for having promoted a view of elements, a dual sense of element. So he embraced the idea of elements as the simplest result of purification and simplification, but he also maintained, and this is even more sort of significant, he said that the periodic system was primarily a classification of the abstract sense of elements. So what does he mean by abstract sense of element? He explained it as unobservable components of the more obvious sense of element. So the obvious sense of element is sometimes called the element as a simple substance. But the element, in inverted commas, as the abstract element, is something that, according to Mendeleev, does not have properties, but is, again, somehow the bearer of all properties. This sounds weird, it sounds metaphysical, it sounds almost spooky, and yet he explains it in the following way. When sodium and chlorine combine together to give sodium chloride, there seems to be no trace of sodium or chlorine in the sodium chloride. So we can ask, in what sense have sodium and chlorine survived in the formation of the compound? Certainly not as simple substances. Otherwise, we'd be able to pick out the sodium and the green gas chlorine. So something has survived in the formation of the compound. Now, that unobservable something, according to Mendeleev, is identified by one single property, its atomic weight. So it's
close.
not that it... Go ahead.
Yeah, so close to what we have today, right? Atomic weight.
The only modification has been that we now realize that we have to replace atomic weight with atomic number.
Mm-hmm.
But still, the identifying criterion for any element is the counterpart of atomic weight. Yes.
It's amazing how close he got. And this is before, I mean, very early in the days of atomic structure, like the knowledge of atomic structure and atomic theory. So, it is quite amazing how he got so close with so little to go on, really. But sorry, I interrupted you.
Not only that, but you bring up a good point. You know, the origins of modern atomic theory. Again, atomic theory was invented by the pre-Socratic philosophers, but they didn't do much with it, we can say. The modern rehabilitation of atomic theory comes about at the hands of John Dalton, a Manchester schoolteacher. There was great opposition to that idea at the time, which would be the early 1800s. Some chemists embraced the idea of atoms literally existing, but many of them did not go along with the idea that atoms actually existed. Now, interestingly, Mendeleev was one of those. Throughout his life, Mendeleev denied the real existence of atoms. And he actually preferred to talk about elemental weight rather than atomic weight in order to deny the existence of atoms.
So that's so interesting. How does he distinguish elemental weight from atomic weight? Or is it just semantics?
Well, it's partly semantics, and it's partly not wanting to accept the idea that these things actually exist as entities. So yes, there are combining weights, if you like, and that's what leads to atomic weights. After all, atomic weights are obtained by analyzing combinations of how much element combines with another element, and so on. But that you're not committed to the belief in literal atoms if you do that. So he accepted the values, but not the philosophical, the added idea of saying, well, and these things literally exist.
Well, that's fascinating. So for his whole life, he never accepted atoms.
No.
Wow. That really is. I never knew that. That's amazing. Coming back to the periodic table, was the periodic table something that was invented, or was it something that was discovered?
It's hard to answer that question. It's both. It's invented because humans had to arrive at that idea. But at the same time, you can call it a discovery because the relationship between different kinds of elements is believed by most people to be somehow really existing out there. We are not imposing that relationship on nature. Although there are debates about this, there are some. This again raises the question of realism and what's sometimes called anti-realism. The realist believes, for instance, that atoms actually exist. The anti-realist, sometimes called instrumentalist, believes that atoms are a useful figment, they're a useful instrument, but they don't literally exist. Mendeleev was of that ilk.
I see. So just
go
we can sort of I imagine from the name instrumentalist, it's these theories almost arise as artifacts from our instruments when we try to measure things and we get numbers out and we try to apply some kind of explanation. We say, okay, this is to do with atoms, but it doesn't necessarily mean that atoms are there if we can't see them.
And there are good reasons for thinking that instrumentalism is the way to go. But think about the fact that entities which were postulated by very successful theories, in chemistry we have caloric, in physics we have the ether, phlogiston in chemistry. Now, these things have not survived. So the people who were realists at the time have a problem explaining that away, because at the time, these entities, such as phlogiston, in the case of combustion, are trying to understand combustion. Phlogiston was successful to some extent in explaining combustion, and yet it's turned out that phlogiston does not really exist. So the argument goes, why should we believe that electrons and protons and neutrons and what have you really exist, just because they happen to do a good job at the moment?
So, that's a really great point. Are we at the point today where we can confidently say they do exist then, with particle accelerators and things like that?
It's a philosophical question.
Yeah.
To some people, yes, because in the case of atoms, it's a little different because there are now supposedly images of atoms. We've all seen them in textbooks, these sort of fuzzy images of a benzene molecule, which looks vaguely hexagonal. But, are those really atoms we're seeing in those fuzzy areas?
It's an amazing question, because I guess we'll never really know for sure. Let's talk about the origins of the discovery of the periodic table. Could you tell me about triads, and were they the first step towards the periodic table?
In a sense, yes. Dalton established atomic weights. And then when a consistent set of atomic weights had been achieved, and then that took some time. That took about 50 to 60 years after Dalton. chemists and other scientists naturally looked at these atomic weights and tried to find relationships between the values. And a German chemist, Wolfgang Dobereiner, came across the idea of chemical triads. The classic example is lithium, sodium, and potassium. But there are many of these sets of three elements in which one of the elements has the average properties, meaning sodium has an atomic weight which is the average of the values of, if you add the value of lithium to the value of potassium and divide by 2, you get approximately the value for sodium. But even more significantly, the chemical reactions of sodium are somewhat intermediate between the chemical reactivity of lithium and potassium. You know, there's the famous experiment that we've all seen in school where you throw a little piece of each of these metals into a bowl of water. Lithium hardly reacts at all. Potassium reacts rather violently. It flips about on the surface, it catches fire. Sodium is somewhere in between. So with a triad, you have for the first time a numerical relationship which is connecting different elements. So this is a hint of some underlying structure, which turns out eventually to be the periodic table. But at that stage, people just recognized isolated sets of three elements called triads.
So following this, the next thing was conjugated triads, right? And was that when we started to connect elements that were not chemically related, but they still found numerical connections between them?
Yeah, so at that point, people began to sort of play with numbers, and some of them lost sight of the importance of the chemistry, and they were just playing with numbers. It became just pure numerology, where you can always find three elements for which one of them will be the average atomic weight of the other two. But if there's no chemical significance in that set of three elements, then it really is just numerology and therefore rather worthless. So yes, people took the idea of triads a little too far, and triads lost their validity, if you like. People became skeptical of the usefulness of triads.
Okay. So people had started to notice these numerical connections between the elements.
Yeah.
The next major step, I suppose, was periodicity. So what is that, and when was that first observed?
Okay. Now, periodicity is a further and more fundamental property whereby if you arrange the elements in order of increasing atomic weight as they did originally, as you move along that sequence, every so often you get an approximate repetition of a previous element. So you have lithium, you move through the atomic weights, you come to sodium, which is similar to lithium, you move again, and you come to potassium, and so on. So this now begins to explain why triads were acting in the way they were, if you like. It's an explanation for triads, and it's the discovery of chemical periodicity. So chemical periodicity is more than just a one-dimensional sequence of elements. It's now a two-dimensional structure, a two-dimensional system, which embodies the fact that elements repeat, approximately, of course, not exactly, after regular sequences.
That's really interesting. So who was it that discovered this or first observed this idea of periodicity? Was it Newlands, de Champ-Courtois?
There were actually at least five discoverers before Mendeleev. The very first was the Frenchman de Champ-Courtois, yeah. And Newlands in London, Odling also working in London, Heinrichs, a Danish chemist who had moved to the United States. I'm forgetting one probably. Oh, Lothar Meyer, a German chemist, but perhaps the most serious competitor to Mendeleev's most successful system of 1869. So over a period of about 7 years, there were 6 independently discovered periodic systems.
So it almost seems like it was inevitable this periodic table was going to come soon in that era. All
Yes,
these people working on it.
yes. Also, we should bear in mind that by that time, more elements had been discovered. It would have been impossible for Dobereiner himself to discover the periodic system because he was short of about 30 elements, if you like. In the succeeding years, in the following years, between Dobereiner and the 5 or 6 discoverers, a number of additional elements were isolated, discovered, and so you had more to play with, and you didn't have as many gaps, if you like, in the periodic table.
That makes a lot of sense. So let's talk about Newlands, because his contribution was quite interesting. Newlands discovered that every 8 elements, the properties seemed to repeat, and he called it the Law of Octaves, which sounds like a beautifully elegant discovery where chemistry seemed to connect with music, of all things. Why were other chemists so against the Law of Octaves at the time? Was it because it was just a bit too elegant and a bit too perfect?
It's hard to put oneself in the place of the chemists who dislike the idea. Some have argued that it's because he made this musical analogy. And all that he was trying to point out was that in the same way that music is periodic, so are the elements. I don't think he meant it literally, that there's some underlying deep connection between chemical periodicity and musical periodicity. It was a revolutionary idea. But so frankly, I don't know, because in retrospect, of course, this all makes sense. But there's great conservatism that runs through science, as well as innovation and new ideas. I mean, that's a topic in itself. Scientists have both aspects to their nature. They will resist change, and rightly so, because it had better be right before you accept a new innovation. But they're also very creative, so that they will entertain new ideas. So on this one, yes, Newlands was unlucky enough to have his idea rejected. He was not an academic chemist. He was an industrial chemist, which may have contributed to the academic chemists sort of turning their nose up at this mere industrialist who was daring to make this suggestion. So yeah, Newlands had it right, and Newlands went, in a sense, deserves extra credit for suggesting that it's a law of nature. So in other words, he put great emphasis on the repetition of elements.
Yeah, it's a shame that he wasn't given more credit at the time, I suppose. It's interesting because in chemistry class at school, we were always taught that Mendeleev was the one who discovered the periodic table, and that was it. But from what we've talked about so far and from reading through your book, it's quite clear that the actual history is a bit more blurry, I guess, with regards to who was the discoverer. In your opinion, which person or persons deserves the most credit?
It's very difficult to say. I would prefer not to assign special credit to any of them. However, we have to remember that it was only Mendeleev who had this deep, I would say, philosophical appreciation for the nature of elements. Going back to what I was saying earlier, the discussion of the dual sense of element as simple substance, and the abstract sense of element, seems to have only been present in the writings of Mendeleev. None of the others concern themselves with the real nature of elements. So the others, including Newlands, looked at the values of atomic weights, noticed the periodicity, but didn't really justify it in any way with an exploration as to the nature of elements, if you like. So, and of course, Mendeleev made predictions. This is usually given as the reason why Mendeleev was the most significant of the discoverers. Mendeleev not only left empty spaces in his periodic table, but predicted that there would be new elements He went as far as predicting what they would be like, down to their specific properties. And furthermore, he was shown to be correct in three significant cases. Scandium, gallium, and germanium, which were discovered in a matter of 15 years, all turned out to have almost exactly the properties Mendeleev had suggested.
There's a great story. Actually, could you tell me about Mendeleev's involvement in the discovery of gallium specifically, and his sort of audacious input that he had there?
Well, in the case of gallium, when it was discovered, I don't remember how many years after Mendeleev had predicted several properties of it, was discovered in France. That's why it's called gallium, after Gaul, the old name for France. The man who discovered it claimed that it had a particular melting point, if I remember correctly. And this disagreed with Mendeleev's prediction as to what the melting point should be. And so Mendeleev, I think, congratulated the man in question. Do you remember who that was, the discovery of gallium? De Bois-Baudran.
Yes.
De Bois-Baudran.
I think it was specific gravity that was the property.
Oh, was it? Okay. So he got the Frenchman reported the specific gravity of his new element, but it conflicted with what Mendeleev had predicted. So Mendeleev had the audacity to say to him in writing, no, I think you may be wrong. Why don't you look again, measure it again, and I think you'll find it to be more like such and such a value. And sure enough, the Frenchman repeated the experiment, and Mendeleev had been right. So this is almost like magic. Mendeleev, miles and miles away in St. Petersburg, knew the properties of this element better, in a sense, than the man who had it in his hands and should have known the properties, if you like.
That is amazing. I can't imagine receiving that letter from Mendeleev and just hearing about this Siberian from thousands of miles away who's questioning your the data that you've published already.
Right.
Must have been quite an affront.
Right. Yes. And you mentioned Siberian because not only was he a Russian, but he was a Siberian that the Russians actually looked down on.
Oh, really? I didn't realize that.
Oh, yes. Mendeleev had trouble getting into university because he was Siberian.
Oh, interesting. So that was why I believe he was rejected from Moscow originally. Is that right? And then accepted into St. Petersburg eventually, or something like that.
Yeah, something of that kind. The university he finally got into had been the university of his father,
who was a teacher,
where his
right?
father had attended. So it was a sort of old boys network type of deal.
Oh, I see. So it's the only reason he got in, sort of nepotism.
Nepotism.
So can you tell me a bit about that famous weekend where he pieced together his periodic table? Because it was already done in just a couple of days, right?
Well, yes and no. The popular story is that he did it over a matter of a few days. The other popular story is that he had a dream where it all appeared to him. But really, he'd been working on this for about 10 years. It's a gradual process. It's never. I mean, sometimes there may be eureka moments when the idea finally appears in a finished form. But I think in the case of Mendeleev, people who've looked into the details have concluded that actually it did not happen over a matter of a few days.
Interesting. Okay, so even his very first periodic table was not just over a few days.
Well, that may have been, but what do you consider to be the discovery? I mean, if it was in his mind and if he was working on a system, should we put a lot of attention on the fact that he finally sat down and wrote it out? Maybe, or was it when it was first published, or was it? We get into sort of endless arguments about what constitutes a discovery.
That is true. That is fair enough. So we often consider, or at least seem to consider, that the way science progresses is in the form of huge leaps made by various geniuses who show up periodically throughout history and just turn the world of science on its head. Do you believe that's what happens? And if so, was Mendeleev one of these geniuses? How significant was this guy?
Okay, I would say Mendeleev was a genius, but I would also say that I disagree with the view of these giant sudden leaps in scientific discovery. This is a view made famous by Thomas Kuhn, the historian and philosopher of science, who wrote a very influential book, The Structure of Scientific Revolutions, where he put a lot of attention on the idea of scientific revolutions, sudden leaps. Now, there have been perhaps a few revolutions, but even in major revolutions, such as the discovery of quantum theory, one can always find precursors. And if you look into the details, you discover that it was not, in fact, a sudden discovery. So similarly, Mendeleev, yes, was a genius for bringing all this together. But here we have the case of 5 people who had discovered chemical periodicity before him, for example. So that's a simple argument against the idea of a dramatic, sudden, and revolutionary leap forward.
Yeah, that's fair enough. I mean, when I started my PhD, anyone who starts a PhD thinks they're going to change the world in the next 3 years when they're doing this PhD. And then you get to the end of it and you realize you've barely scratched the surface in anything. So I kind of went through the same change in mindset as what you've just described. You think a huge leap is going to occur, but then you realize that it's actually extremely incremental and everyone's just kind of standing on the shoulders of everyone else.
Right.
Um,
I've written a book on this subject, by the way. It's called A Tale of 7 Scientists.
oh yeah, tell me about that.
Well, it's 7 scientists who are not directly involved in the discovery of the periodic table, but sort of somewhat tangential, who were very little known at the time, or even now, they're very little known. They're hardly ever mentioned in histories of chemistry and physics, and yet made absolutely fundamental discoveries that can be now seen as important steps towards the eventual mature discovery or theory. John Nicholson was a physicist, a mathematical physicist working in England, who was the first to quantize angular momentum, for example, an idea that Niels Bohr adopted and adapted into his famous Bohr model of the atom.
Wow.
It turns out the original version of the Bohr model of the atom didn't have the quantization of either energy or angular momentum. So there are many cases like this, and I focused on 7 such cases.
Wow. So these are kind of like the supporting cast
Yes.
throughout science. They're sort of not quite as well appreciated as the big names, but they are extremely important nonetheless.
Yes.
With all the research you've done throughout your career, are there any original documents and sources that you've physically handled that have left you feeling sort of awestruck from their significance? Anything from Mendeleev or anything like that?
I've never handled any original Mendeleev materials, and no, I've not tended to do archival work in that sense. I've tended to work with, for instance, I mentioned Niels Bohr. Of course, I've read through the original papers of Niels Bohr, but it's not because I was handling a handwritten document or something like that.
Okay. I wanted to show you this, speaking of sort of not quite original documents, but I've got this book here, which is William Ramsay's Gases of the Atmosphere. It's his second edition, which was so the first edition was published just after he discovered argon, and he talks all about the history of the discovery of the gases in the atmosphere up to and including his own discovery of argon and how he discovered it and how it doesn't seem to fit anywhere. The second edition was published a few years later. This was published in 1902, and since then, he'd discovered all of the other noble gases. So the second edition is this amazing update with all these new elements that had been discovered. And this was published, I believe, 2 years after Ramsay's meeting with Mendeleev, where he convinced him essentially, or they agreed together to add an 8th group to the periodic table. And he's included in here a periodic table with 8 groups, but there's also this slip that kind of folds over so that it can kind of change what the periodic table is depending on the position of the slip. He says in the book, the subdivision produced by folding the loose slip is intended to show that the elements represented on it have a double set of resemblances. So I'd never seen this before. I was wondering if you'd seen anything like this before, this slip, and if you knew what the origin was.
I've never seen it. This is extremely interesting because for quite some time now, I've been trying to get to the bottom of when did Ramsay propose to Mendeleev this idea of a group, what we now call the noble gas group. And it's been extremely difficult to find an answer to that question. And so now you're saying that this book is dated 1902.
Correct, yeah.
Okay. So somewhere...
sorry, no, 1900. That's my mistake. The preface is from December 1900.
Good, because I was just going to say that in at least one of my books, I say something like, in the year 1900, Ramsay met Mendeleev at a conference and suggested to him the idea of an 8th column, which Mendeleev readily accepted because it basically rescued his periodic table, which had been in danger of falling apart because initially no one could find a place for argon, and the problem became worse when 4 or 5 of these mysterious noble gases had been discovered. So no, and I'm very interested to maybe work with you on this sometime, since I have no knowledge of this slip of paper. By the way, what elements is he connecting together in a dual fashion with this slip of paper?
So I'll show you what's in group 5 here. So currently there's nitrogen, phosphorus with the slip in place. It then goes to vanadium, niobium, neodymium, tantalum. Yeah. So that's the group 5 with the slip. But then you can move the slip, and now group 5 is nitrogen, phosphorus, arsenic, antimony, erbium, bismuth. It's interesting because it's not as if moving the slip moves elements to different groups. It just kind of hides elements. So
So I think I understand what he's doing. He's making what we would now call a connection between an 8-column table. The original tables were 8 groups, and what the currently used periodic table, which is an 18-column table. And that's why the transition metals can be included into, you were talking about group 5 in one case, and removed from group 5, or what we now call group 15, actually, the nitrogen, phosphorus, etc. group. So this doesn't really pertain to the noble gases, or does it? Does this have any bearing on the question of the noble gas group?
Well, actually, so the slip overlaps with group 8 as well. And so without the slip, we've got the normal, what we would expect from the noble gases, helium, neon, argon, krypton, xenon. Right. And then question mark, where he's left gaps for potential noble gases to be discovered in the future. But then if you overlay the slip on top, now he's got a load of transition metals. So iron, cobalt, nickel, ruthenium, rhodium, palladium, osmium, iridium, platinum.
Very interesting, because those were in the original group 8 of Mendeleev and many other co-discoverers. Yeah. This, thank you for pointing this out. This, I think, deserves a lot more attention and maybe an article or two.
Yeah, for sure. We can talk about it later after this. I will send you pictures of it.
You've reminded me of the importance of archival research, and maybe it's something I could have done more of.
I'm glad to hear it. So the publication year for this was 1902, but for the preface to the second edition, it says December 1900. So I'm not exactly sure when it was. I guess it was around about then.
Right.
when it was published. But it's really interesting. We'll talk about it more after this, I think.
Sure.
But if anyone's watching and wants to hear more, then let me know in the comments and we can potentially make a video about this in the future. So you mentioned that today we have this 18 group periodic table. When did we go from 8 groups to 18 groups?
Well, I think you're identifying it.
Wow.
You're producing some of the evidence for a more detailed account of that question. One of the early 18-column tables is due to the Swiss chemist Werner. I think it's Alfred Werner. Again, early 1900s, where he was beginning to produce these extended periodic tables. Because the elements such as ruthenium and rhodium and so on were originally in the original group 8 of Mendeleev, but now they're incorporated into the main body of the table in the transition element block, in the D block. So yes, I can't give you a definitive answer, but what you have come across there, it will contribute to that story.
Amazing. That's really cool. So this Ramsay one might be some kind of intermediary between the 8 and the 18.
Yes, because he doesn't seem to have realized that you can avoid that slip of paper in a way by moving to an 18-column table. So it would be nice to contrast this with the eventual 18-column table. And then look into whether Ramsay had any correspondence with Werner and so on.
That's amazing. I can't wait to find out more about this. That's so interesting. Since this era, since the beginning of this journey, there have been hundreds of attempts at creating a periodic table, and I'm sure you've seen pretty much all of them. Discarding or disregarding their scientific merits, what are some of your favorite iterations of the periodic table, purely from a visual or artistic standpoint? Because there are so many different types. Are there any that you just like the look of?
Oh, well, I've seen a lot of them, but I can't think of one offhand that I would especially. Well, I will give credit to one which was designed by a friend of mine who sadly passed away a couple of years ago, Philip Stewart, an Oxford. He was actually a biologist of sorts, but with a deep interest in all sorts of other subjects. And it's the galaxy periodic table. Because one thing that the regular periodic tables fail to emphasize is the continuous nature of the sequence of elements. It's as if one drops off at the right margin of the periodic table or the left margin. But in fact, it's a continuous loop, or it's a continuous galaxy. So Philip Stewart's periodic table actually makes it into a galaxy.
Oh, wow. That is so cool. There's real artistic value to it, as well as
yeah.
Oh, it looks really cool.
Yeah.
It just works. It just seems to work so well.
Yeah. And so the groups are found by going radially from the center outwards. And incidentally, one of the very early discoverers who we mentioned earlier, Heinrichs, the Dane working in America, he had a periodic table which was of essentially this form of being a spiral periodic table.
Yes, with the groups kind of on these
on the spokes of the wheel
coming out.
Yeah.
So here we are today, over a century and a half since Mendeleev first started working on the periodic table. Is the periodic table now complete? Have we completed chemistry? And if not, what's left to do?
Well, those are two separate questions. No to the second one, of course. But have we completed the periodic table? By a strange coincidence, the periodic table for the first time, in a sense, is complete because there are no empty spaces. However, it is very unlikely to be really complete because we are currently on the verge of the discovery of elements 119 and 120. And as soon as that happens, one has to open up a new row or period in the periodic table, which will have initially one or two elements. So at that point, it will be far from being complete. But with the discovery of those last four super heavy elements, which included things like nihonium and tennessine and organesian, I always hesitate because the man is called organesian and the element is called organeson. So with the discovery of organeson and those elements, it really seems to be complete.
That's so cool. So once these two new elements are discovered, we're kind of opening this can of worms where that kind of means there's going to be an entire, a dozen extra elements to discover it eventually?
Well, more than a dozen, actually. It'll be, because those periods will be 50 elements wide.
50?
50.
Wow. So will we ever get to the end of that?
No way. Briefly put, no.
Okay.
It becomes more and more unstable, more and more difficult to create. And even when they are created, they last for such a short period of time that it just becomes a sort of exercise in, can we do it?
Right, yeah.
And it has some scientific value because we can test theories of quantum and relativistic quantum theories of atoms in these extreme cases, but certainly no possible applications to these very short-lived elements.
Yeah, it's really in the realm of physics rather than chemistry there, isn't it?
Yeah, a bit of both.
Yeah. Eric, thank you so much for your time today and for all the incredible work you've done throughout your career. I'm looking forward to featuring you more on the channel in the future, if you're willing to return.
It's been fun, and we've made a step forward, I think, with your second edition Ramsay.
I know, yeah, I was really happy about that. We've had a very academically productive conversation, which I wasn't expecting in that way. Where should people go if they want more from you?
Well, my website, ericscerri.com.
Yeah, everyone, please go and support Eric's work. Check out his book and books, multiple, if you want to learn more. I read the periodic table book in preparation for this video, and it's fantastic. I can't even tell you how much I learned. It's so detailed. It's really great. Eric, thanks again. Thanks for watching the first episode of the Chemistorian podcast. This is the first time I've ever done anything like this, so let me know what you thought in the comments, and before you go, I want to ask for your help. Every one of my videos is an enormous project that I make by myself in my free time, but I want to be able to divert more time and energy to videos like this, and your support can make that happen. If you consider liking, subscribing, commenting, sharing, etc., that would tell the YouTube algorithm that this video is worth watching, and it would really help me out. My goal is to get to 100,000 Chemistorians by the end of 2025, so if you made it this far and you want to help out the channel, I'd really appreciate your support. Also, I recently started a Patreon if you're interested in supporting the channel further. Become a patron to unlock perks such as bonus videos, ad-free videos, early access, behind-the-scenes updates, Q&As, and more. Thanks for watching, and I'll see you in the next one.